Today's topic will be an introduction into enumerators. Enumerators, or recursively enumerable languages, are Turing machines with an attached printer. The following model can be used to show how an enumerator works. With this model, we're going to have a control. This control is going to be redirected to the printer, and on this printer, we're going to have our string of inputs with the following tape. The following tape will contain AA, AABA, and ABBA. Once we have our printer, we also have our working tape. In this working tape, we'll have the following zeros and ones. This, as I said, is our working tape. The way that this works is that the Turing machine can use that printer as an output device to print strings. Every time the Turing machine wants to add a string to the list, it sends the string to the printer. As you can see here, the following strings are AA, AABA, and ABBA. However, before we touch more specifically on enumerators, we have to understand the bigger subset of languages under which enumerators fall. The first one are recursive enumerable languages, or RE, or type 0 languages. The reason that they are called type 0 languages is because they are generated by type 0 grammars. These languages can be accepted or recognized by the Turing machine, which means they will enter into the final state for the strings of languages, or may not enter into the rejecting states for the strings which are not a part of the language. Another type of language is REC, or recursive languages. These languages are decided by the Turing machine as they will enter into the final state for the strings of languages or rejecting states for the strings which are not a part of the language. Basically, these languages can be described as the following. A language is recursive if a Turing machine accepts yes or no. If a given string is part of this language, if we lift this requirement to merely say yes for the strings of the language, then the following will happen. We're going to have a recursive enumerable language. And the reason that this happens is, as we stated, we're going to lift the requirement to not accept no. It will now only accept yes, which is why it's recursive and enumerable as opposed to recursive. The following relationship can be established with this diagram, where we have RE, or recursive enumerable languages, on the outside, and then recursive languages on the inside. Therefore, every recursive language is recursively enumerable, but not every recursive enumerable is recursive. If we want to apply this to what we've been learning in class, we can take this a step further and look at the relationship between recursively enumerable languages, context-free languages, and regular languages. The following figure will establish this relationship, where we have recursively enumerable on the outside. Then within that, we have context-free languages. And then finally, at the smallest level, we have regular languages. The reason that this occurs is because regular languages have characteristics that can be found exclusively within that, and then as you get bigger and bigger, the requirements needed for each languages are lesser. Now that we have our introduction into enumerators, we can begin to look at our formal definition that we'll be using for the following two theorems. In terms of a formal definition for enumerators, we're going to be using the one that was described in the textbook and has been used and found in various online sources. Enumerator E is going to be represented by a two-tape Turing machine. One working tape and one print tape. It can be defined by a 7-tuple following the notation of a Turing machine. This is going to look like as the following. This enumerator is going to have a print state and then a rejection state. Now, if you were to look at each individual part of the tuple, it's going to look as the following, where Q is going to be a finite and non-empty set. The second part is going to be finite, and it is also going to be a non-empty set of the working and printing alphabet. The third part is going to be very different. This one is going to look more specifically, even though it is finite, it's going to look at the set of the working tape. And what that's going to be is right there. This is going to be our transition function, and our transition function is also going to model the definition that was given in the textbook for enumerators. Now we're going to look at our start state, which is going to be represented by the following. And as I mentioned, that is going to be our start state. Finally, we're going to look at our print state and then our rejection state. Our print state, qprint, and then our rejection state, which is qreject. And to elaborate on that further, that's going to be when qprint does not equal qreject. Now that we have our formal definition of enumerators, we can begin to look at a couple of theorems that we found. The first theorem is going to be the equivalence of enumerator and Turing machines. This is going to be theorem 3.21 as found in the textbook. What this theorem is trying to prove is that a language is Turing recognizable if and only if some enumerator enumerates it. So what that's going to be is Turing recognizable if some enumerator accepts. So what our proof is going to look like in this theorem will be as the following. We have to show that we have an enumerator E that enumerates language A Turing machine M recognizes A, and following, the Turing machine M will work the following way. How this Turing machine is going to look like is M is going to equal on output, or actually on input W, the first condition will be that run E. We are going to run E every time that E outputs a string, and we're going to compare it with W. So what that looks like is run E on output, and then as I mentioned, we're going to compare to W. The second condition for this proof is going to be if W ever appears in the output of E, then accept. If W appears in output, accept. And that is how we have reached our accept state. Clearly, M accepts those strings that appear on E's list. Now we do the other direction. If Turing machine M recognizes language A, we can construct the following enumerator, E for A, and we say that S1, S2, and S3 and so forth is a list of all the possible strings of E. Finally, what happens if we ignore the output or the input? Now, if we look at this, if we want to ignore the input for this theorem, the following requirements must be met. First, we're going to repeat the following for I. And what that's going to be is we are going to repeat 1, 2, 3, and so forth. The second step will be that we run m for I steps on each output that we wrote here, which is the list of strings S1, S2, and S3. So we are going to run m for I steps on each input. And as I mentioned, that input is going to be the list of strings that are going to be found in E. S1, S2, and S3, and so forth. Our third step is, if any computation accept, print out accordingly. If accepted, then we print. This is the two requirements that have to be met. M on output W and E if we are going to ignore the input for the following theorem that proves that a language is turning recognizable if and only if some enumerator enumerates it.
Okay, so going off of what Omar said when discussing the definition of enumerators and recursively enumerable languages, this comes into play when discussing another core concept in computer theory, which is the decision problem. So the decision problem basically states that given some input fed into some algorithm, will this problem either accept as an output yes or reject as an output no? And if the algorithm doesn't come to a concrete answer, as in it just loops infinitely, we say that no, it is not decidable. But if it does either accept or reject, we say yes, it is a decidable problem. An example of this could be, a very simple example, it could be, given some number x, can you decide if this is a prime number or a composite number? So let's make x equal to 8, and very simply we feed that into this algorithm, which would basically just pick numbers less than 8 and divide by it until it comes up with a number, a concrete answer. So 8 divided by 7 is not a whole number, 8 divided by 6 is not a whole number, 8 divided by 5 is not a whole number, 8 divided by 4 is yes, a whole number. So it will accept 4, stop the algorithm, and pick yes. So very plainly, that's an example of a decidable problem. Thanks. So using the concept of determining if a problem is decidable or not, we can apply the use of a recursively enumerable problem by first discussing the realms in which this would occur. So on the outside you have recursively enumerable languages, which can be decided through the means of using an enumerator, and then within that you have context-free languages, which can be decided using a push-down automata, and then within that you have regular languages, which simply be decided using finite automatas. So a key decidable problem when discussing recursive enumerable languages is the mortality problem, which is that Given some Turing machine, can you decide whether or not this Turing machine will halt on any possible string that's fed into it? So normally there's no concrete algorithm to solve this problem for any general Turing machine, which is why it wouldn't fall into the category of regular languages or context-free languages. However, if we flip this Turing machine into its enumerator counterpart and input and have it run every possible combination of strings on that Turing machine and check if it halts and outputs a string every single time, then we can decide if this Turing machine falls into the category of mortal. So essentially, how this would work is, given this Turing machine variant E, which is the enumerator, you feed into it the symbols Q, which is one of the machine states in this Turing machine, and W, which is any possible combination in an infinite set of strings. And essentially, given those two inputs, this enumerator should output on its printer whatever W is, like any possible infinite string. So it could be 0, 0, 1, 0, 1, 0, etc. Infinitely long. And so we see how recursively enumerable languages are important because they can help decide problems that would normally you wouldn't be able to figure out if it's decidable or not. So another example of a key decidable problem in computer theory is the post-correspondence problem. And this problem essentially works in this way, which is given a set of domino pairs. For example, let's have this be in the set, this be in the set, and this be in the set. We want to decide that given this set of dominoes, can we rearrange it in a certain way in which the numerator, or all the symbols on the top, will be equivalent to the denominator, all symbols on the bottom. And for example, given this set here, we can also represent the dominoes on a table. We have A representing the numerators, B representing the denominators, and we'll have the first domino in the set in the first row, second domino in the set in the second row, and the third domino in the set in the third row. So essentially, you could arbitrarily just try all possible combinations in a brute force approach until you find the order that has the numerator equal to the bottom, and it could be as such. I'll randomly choose 2 as my first selection, have that on the top, so that's the first choice, and this is the bottom. Then I'll choose domino 1, U on top, and U on bottom. Then I'll choose domino 1 again, and have U on top and U on bottom. And then lastly I'll choose domino 3, and U on top and U on bottom. So we see how after rearranging the set in such a way, the numerator is equivalent to the denominator. So the question here is there a way to determine how, given an arbitrary set of dominoes, is there a solution in which you can rearrange the set such that the top is equal to the bottom? And in order to figure out this solution, let's look at another example. Let's see, example 2. I'll write this out in its table representation. You have a set of numerators on the left column. We'll make a 1, 0. Okay, so first off, in order for the top to match the bottom, we would have to have our first domino in the set be one that contains an equivalent first character in its numerator and denominator. So we would have to pick domino 1 over here because the first character in both the numerator and the denominator match. So let's throw our solution here, and let's have 1 be the first one we select. Okay, so now we need a 1 on the top because that's the next character on the bottom. So we have to either pick 3 or 1 again. So let's try 3. 1, 0, 1. Okay, still doesn't match, but now we have to pick one that has 1 on the top and would have the next one equivalent. So let's try 1 again. Oops, we actually can't use 1. Let's try 3 again. Oh, but now we're in a loop because you see how we're essentially in the same set in which we have to pick 3 again. So this solution wouldn't work. We cross that out. We try again. We could have A, B, pick 1 again, we'll have 1, 0, 1, 0, 1, and this time I'll pick 1 again, we'll have 1, 0, oh, we can't have 1. So yeah, so you see how essentially through just through inductively searching through the first possible combinations, we can't have like a set that has the top match the bottom, but we don't know that for sure because it's possible if we keep following along this process and we just keep tagging on more dominoes in this set, like 3, 0, 1, and so on, and we just keep that process going. We may eventually find a combination that satisfies the problem. So, however, this problem is not recursively enumerable because if you were fed these inputs into an enumerator, let's have this be enumerator E, you feed in whatever your sets of dominoes, we don't know whether or not this numerator will halt because it could just continue on following our example here, just arbitrarily randomly selecting orders of dominoes and just never halting. So therefore we can say this problem is not decidable, and it is not decidable because it is not recursively enumerable, which ties back into what was said before when determining if a problem is decidable or not. We use enumerators and recursively enumerable languages to determine whether or not a problem is decidable.